Little Ice Age. Global average temperatures show that the Little Ice Age was not a distinct planet-wide period but a regional phenomenon occurring near the end of a long temperature decline that preceded recent global warming. The Little Ice Age (LIA) was a period of regional cooling, particularly pronounced in the North Atlantic region. It was not a true ice age of global extent. The term was introduced into scientific literature by Francois Mathis in 1939. The period has been conventionally defined as extending from the 16th to the 19th centuries. But some experts prefer an alternative timespan from about 1300 to about 1850. The NASA Earth Observatory notes three particularly cold intervals. One began about 1650, another about 1770, and the last in 1850, all of which were separated by intervals of slight warming. The Intergovernmental Panel on Climate Change Third Assessment Report considered that the timing and the areas affected by the LIA suggested largely independent regional climate changes, rather than a globally synchronous increased glaciation. At most, there was modest cooling of the northern hemisphere during the period. Several causes have been proposed: cyclical lows in solar radiation, heightened volcanic activity, changes in the ocean circulation, variations in Earth's orbit and axial tilt, orbital forcing, inherent variability in global climate, and decreases in the human population, such as from the massacres by Genghis Khan, Black Death, and the epidemics emerging in the Americas upon European contact. Areas involved. The Intergovernmental Panel on Climate Change Third Assessment Report, TAR, of 2001 described the areas that were affected. Evidence from mountain glaciers does suggest increased glaciation in a number of widely spread regions outside Europe prior to the 20th century, including Alaska, New Zealand, and Patagonia. However, the timing of maximum glacial advances in these regions differs considerably, suggesting that they may represent largely independent regional climate changes, not a globally synchronous increased glaciation. Thus, current evidence does not support globally synchronous periods of anomalous cold or warmth over this interval, and the conventional terms of Little Ice Age and Medieval Warm Period appear to have limited utility in describing trends in hemispheric or global mean temperature changes in past centuries. Viewed hemispherically, the Little Ice Age can only be considered as a modest cooling of the northern hemisphere during this period of less than 1 degree Celsius relative to late 20th century levels. The IPCC Fourth Assessment Report, AR4, of 2007 discusses more recent research and gives particular attention to the medieval warm period. When viewed together, the currently available reconstructions indicate generally greater variability in centennial timescale trends over the last 1 quire than was apparent in the TAR. The result is a picture of relatively cool conditions in the 17th and early 19th centuries and warmth in the 11th and early 15th centuries, but the warmest conditions are apparent in the 20th century. Given that the confidence levels surrounding all of the reconstructions are wide, virtually all reconstructions are effectively encompassed within the uncertainty previously indicated in the TAR. The major differences between the various proxy reconstructions relate to the magnitude of past cool excursions, principally during the 12th to 14th, 17th, and 19th centuries. North America. February from the calendar of the Trace Riches du Duc de Berry, 1412 to 1416. Early European explorers and settlers of North America reported exceptionally severe winters. For example, according to Lamb, Samuel Champlain reported bearing ice along the shores of Lake Superior in June 1608. Both Europeans and indigenous peoples suffered excess mortality in Maine during the winter of 1607 to 1608, and extreme frost was meanwhile reported in the Jamestown, Virginia, settlement. Native Americans formed leagues in response to food shortages. The Journal of Pierre de Troyes, Chevalier de Troyes, who led an expedition to James Bay in 1686, recorded that the bay was still littered with so much floating ice that he could hide behind it in his canoe on 1 July. In the winter of 1780, New York Harbor froze, which allowed people to walk from Manhattan Island to Staten Island. The extent of mountain glaciers had been mapped by the late 19th century. In the north and the south temperate zones, equilibrium line altitude, the boundaries separating zones of net accumulation from those of net ablation, were about 100 meters, 330 feet, lower than they were in 1975. In Glacier National Park, the last episode of glacier advance came in the late 18th and the early 19th centuries. In 1879, the famed naturalist John Muir found that Glacier Bay ice had retreated 48 miles, 77 kilometers. In Chesapeake Bay, Maryland, large temperature excursions were possibly related to changes in the strength of the North Atlantic thermohaline circulation. Because the Little Ice Age took place during the European colonization of the Americas, it discouraged many early colonizers, who had expected the climate of North America to be similar to the climate of Europe at similar latitudes. They found that North America, at least in what would become Canada and the northern United States, had hotter summers and colder winters than Europe. That effect was aggravated by the Little Ice Age, and unpreparedness led to the collapse of many early European settlements in North America. Historians agree that when colonists settled at Jamestown, it was one of the coldest periods in the last 1,000 years. Drought was also a problem in North America during the Little Ice Age, and the settlers arrived in Roanoke during the largest drought of the past 800 years. Tree ring studies by the University of Arkansas discovered that many colonists arrived at the beginning of a 7-year drought. The droughts also decreased the Native American populations and led to conflict because of food scarcity. English colonists at Roanoke forced Native Americans of Assiniboine to share their depleted supplies with them. That led to warfare between the two groups, and Native American towns were destroyed. That cycle would repeat itself many times at Jamestown. The combination of fighting and cold weather also led to the spread of diseases. The colder weather helped the parasites brought by Europeans and mosquitoes to develop faster. That in turn led to many malaria deaths among Native Americans. In 1642, Thomas Gorges wrote that between 1637 and 1645, colonists in Maine, then part of Massachusetts, experienced horrendous weather conditions. In June 1637, temperatures were so high that numerous European settlers died. Travelers were forced to travel at night to stay cool. Gorges also wrote that the winter of 1641 to 1642 was piercingly intolerable and that no Englishman or Native American had ever seen anything like it. He also stated that the Massachusetts Bay had frozen as far as one could see, and that horse carriages now roamed where ships used to be. He stated that the summers of 1638 and 1639 were very short, cold, and wet, which compounded food scarcity for a few years. To make matters worse, creatures like caterpillars and pigeons fed on crops and devastated harvests. Every year about which Gorges wrote featured unusual weather patterns, including high precipitation, drought, and extreme cold or heat. Many inhabitants of North America had their own theories about the extreme weather. The colonist Ferdinando Gorges blamed the cold weather on cold ocean winds. Humphrey Gilbert tried to explain Newfoundland's icy and foggy weather by saying that the earth drew cold vapors from the ocean and drew them west. Many others had their own theories for North America being so much colder than Europe. Their observations and hypotheses offer insight on the Little Ice Age's effects in North America. 66. Possible causes. Scientists have tentatively identified 7 possible causes of the Little Ice Age: orbital cycles, decreased solar activity, increased volcanic activity, altered ocean current flows, fluctuations in the human population in different parts of the world causing reforestation or deforestation, and the inherent variability of global climate. Orbital cycles. Orbital forcing from cycles in the Earth's orbit around the Sun has for the past 2,000 years caused a long-term Northern Hemisphere cooling trend, which continued through the Middle Ages and the Little Ice Age. The rate of Arctic cooling is roughly 0.02 degrees Celsius per century, 140. That trend could be extrapolated to continue into the future and possibly lead to a full ice age, but the 20th century instrumental temperature record shows a sudden reversal of that trend, with a rise in global temperatures attributed to greenhouse gas emissions. Solar activity. The Maunder minimum in a 400-year history of sunspot numbers. Sunspot number compared with Northern Hemisphere, NH, temperature anomaly. The upper panel shows 11-year smooth group sunspot numbers from telescopic observations and the sunspot number derived from carbon-14 cosmogenic isotope abundances in tree trunks. The lower panel shows the Northern Hemisphere, NH, temperature anomaly, relative to the 1990 level, from a wide variety of paleoclimate proxies. The black line is the mean value, and the colors give the uncertainty probability distribution. The blue dots are the instrumental record. The dashed lines mark the start and end of the Little Ice Age, LIA, defined by the NH, temperature anomaly level minus 0.16 degrees Celsius. All data sources are described in references. Solar activity includes any disturbances on the Sun such as sunspots and solar flares associated with the variable magnetic field of the solar surface and solar atmosphere, corona. Because Alfvén's theorem applies, the coronal magnetic field is dragged out into the heliosphere by the solar wind. Irregularities in this heliospheric magnetic field shield Earth from galactic cosmic rays by scattering them, which allows scientists to track solar activity in the past by analyzing both the carbon-14 or beryllium-10 isotopes generated by cosmic rays hitting the atmosphere and which are deposited in terrestrial reservoirs such as tree rings and ice sheets. In the intervals 1400 to 1550, the Sporer minimum, and 1645 to 1715, the Maunder minimum, there were very low recorded levels of solar activity, and they are both within, or at least overlapped with, the LIA for most definitions. However, solar activity deduced from cosmogenic isotopes was as high between the Sporer minimum and the Maunder minimum as it was in about 1940, yet this interval is also within the LIA. Hence, any relationship between solar activity and the LIA is far from a simple one. A drop in solar activity circa 1230 AD is measured by biogenic silica-corrected ignition residue, IRBC, has been suggested by one study as a forcing potentially responsible for initiating the LIA, with the authors noting that this drop in solar output preceded the onset of significant volcanism. A study by Dmitry Mokhoy et al. Confirmed that at the beginning of the Sporer minimum, the carbon-14 production rate rose rapidly. These authors argued this rise coincided with a sharp drop in temperatures deduced from European peat bogs. This temperature drop is also seen in mean northern hemisphere temperatures deduced from a wide variety of paleoclimate indicators, but the timing of the onset of the Sporer minimum is actually some 50 years earlier. A 50-year response lag is possible but is not consistent with subsequent variations in inferred solar activity and average northern hemisphere temperature. For example, the peak in solar activity between the Sporer minimum and the Maunder minimum is 50 years after the only peak in average northern hemisphere temperature that it could be associated with. A study by Judith Lean in 1999 also pointed to a relationship between the Sun and the Little Ice Age. Her research found that there was a 0.13% total solar irradiance, TSI, increase over 1650 to 1790, which could have raised the temperature of the Earth by 0.3 degrees Celsius. In the calculated correlation coefficients of the global temperature response to their reconstruction of the solar forcing over 3 different periods, they found an average coefficient of 0.79, i.e. 62% of the variation could be explained by the TSI, which indicates a possible relationship between the two components. Lean's team also formulated an equation in which the temperature change is 0.16 degrees Celsius increase in temperature for every 0.1% increase in total solar irradiance. However, the main problem with quantifying the longer-term trends in TSI lies in the stability of the absolute radiometry measurements made from space, which has improved since the pioneering work of Judith Lean discussed above, but still remains a problem. Analysis comparing trends in modern observations of TSI and cosmic ray fluxes shows that the uncertainties mean that it is possible that TSI was actually higher in the Maunder minimum than present-day levels. But uncertainties are high with best estimates of the difference between the modern-day TSI and the Maunder minimum TSI in the range plus or minus, but with an uncertainty range of plus or minus. At the center of the LIA, during the Sporer minimum and the Maunder minimum, sunspots were minimal and cosmogenic isotope deposition, carbon-14 and beryllium-10, was increased in these minima as a result. However, detailed studies from multiple paleoclimate indicators show that the lower northern hemisphere temperatures in the Little Ice Age began before the start of the Maunder minimum but after the start of the Sporer minimum and persisted until after the Maunder minimum, and even after the much weaker Dalton minimum, had ceased. The return to more active solar conditions between these two grand solar minima had no obvious effect on either global or northern hemisphere temperatures. The central England temperature provide evidence that low solar activity may have contributed to the LIA through the increased occurrence of cold winters, at least in Europe, but colder summers are more correlated with volcanic activity. Comparison of TSI records with Greenland ice core Delta 180 trends suggests that solar activity only accounted for 55% of the observed trend variance. Numerical climate modeling indicates that volcanic activity was the greater driver of the overall lower temperatures in the LIA, as seen in a variety of paleoclimate proxies. Volcanic activity. In a 2012 paper, Miller et al. Linked the Little Ice Age to an unusual 50-year-long episode with 4 large sulfur-rich explosive eruptions, each with global sulfate loading greater than 60 Tg, and notes that large changes in solar irradiance are not required. Throughout the LIA, there was heightened volcanic activity. When a volcano erupts, its ash reaches high into the atmosphere and can spread to cover the whole Earth. The ash cloud blocks out some of the incoming solar radiation, which leads to worldwide cooling for up to 2 years after an eruption. Also emitted by eruptions is sulfur in the form of sulfur dioxide. When sulfur dioxide reaches the stratosphere, the gas turns into sulfuric acid particles, which reflect the sun's rays. That further reduces the amount of radiation reaching the Earth's surface. A recent study found that an especially severe tropical volcanic eruption in 1257, possibly Mount Samala's pre-caldera edifice of the active Rinjani, near Mount Rinjani, both in Lombok, Indonesia, followed by 3 smaller eruptions in 1268, 1275, and 1284, did not allow the climate to recover. That may have caused the initial cooling, and the 1452/1453 mystery eruption triggered a second pulse of cooling. The cold summers can be maintained by sea ice/ocean feedbacks long after volcanic aerosols are removed. Other volcanoes that erupted during the era and may have contributed to the cooling include Billy Mitchell, circa 1580, Wainaputina, 1600, Mount Parker, 1641, Long Island, Papua New Guinea, ca. 1660, and Laki, 1783. The 1815 eruption of Tambora, also in Indonesia, blanketed the atmosphere with ash, and the following year came to be known as the year without a summer, when frost and snow were reported in June and July in both New England and Northern Europe. Ocean circulation. Thermohaline circulation or oceanic conveyor belt illustrated. In the early 2000s, a slowing of thermohaline circulation was proposed as an explanation for the LIA, specifically, through the weakening of the North Atlantic Gyre. The circulation could have been interrupted by the introduction of a large amount of fresh water into the North Atlantic and might have been caused by a period of warming before the LIA that is known as the medieval warm period. Some researchers have thus classified the LIA as a Bond event. In 2005, there was some concern that a shutdown of thermohaline circulation could happen again as a result of the present warming. More recent research indicates that the overall Atlantic meridional overturning circulation may already be weaker now than it was during the LIA, or perhaps even over the past millennium. While there is still a robust debate about the present-day AMOC strength, 163, these findings make the link between AMOC and the LIA unlikely. However, some research instead suggests that a far more localized disruption of the North Subpolar Gyre convection was involved in the LIA. This is potentially relevant for the near future, as a minority of climate models project a permanent collapse of this convection under some scenarios of future climate change. Decreased human populations. Some researchers have proposed that human influences on climate began earlier than is normally supposed, see early Anthropocene for more details, and that major population declines in Eurasia and the Americas reduced that impact and led to a cooling trend. The Black Death in Europe. The Black Death is estimated to have killed 30% to 60% of the European population. In total, the plague may have reduced the world population from an estimated 475 million to 350 to 375 million in the 14th century. It took 200 years for the world population to recover to its previous level. William Rudiman et al. Proposed that those large population reductions in Europe, East Asia, and the Middle East caused a decrease in agricultural activity that allowed reforestation to cause additional carbon dioxide uptake from the atmosphere, leading to LIA cooling. Mongol invasions. A 2011 study by the Carnegie Institution's Department of Global Ecology asserts that the Mongol invasions and conquests, which lasted almost 2 centuries, contributed to global cooling by depopulating vast regions and replacing cultivated land by carbon-absorbing forest. Destruction of native populations and biomass of the Americas. William Rudiman further hypothesized that a reduced population in the Americas after European contact started in the 16th century could have had a similar effect. In a similar vein, Koch and others in 1990 suggested that as European conquest and disease brought by Europeans killed as many as 90% of indigenous Americans, around 50 million hectares of land may have returned to a wilderness state, causing increased carbon dioxide uptake. Other researchers have supported depopulation in the Americas as a factor and have asserted that humans cleared considerable amounts of forest to support agriculture there before the arrival of Europeans brought on a population collapse. Richard Neville, Robert Dahl and colleagues further suggested not only that anthropogenic forest clearance played a role in reducing the amount of carbon sequestered in neotropical forests but also that human-set fires played a central role in reducing biomass in Amazonian and Central American forests before the arrival of the Europeans and the concomitant spread of diseases during the Columbian Exchange. Dahl and Neville calculated that reforestation in the tropical biomes of the Americas alone from 1500 to 1650 accounted for net carbon sequestration of 2 to 5 pg. Brearley conjectured that the European arrival in the Americas caused mass deaths from epidemic disease, which caused much abandonment of farmland. That caused much forest to return, which sequestered more CO2. A study of sediment cores and soil samples further suggests that CO2 uptake via reforestation in the Americas could have contributed to the LIA. The depopulation is linked to a drop in CO2 levels observed at La Dome, Antarctica. Population increases at mid to high latitudes. It is suggested that during the Little Ice Age, increased deforestation had enough effect on the Earth's albedo, reflectiveness, to cause regional and global temperature decreases. Changes in albedo were caused by widespread deforestation at high latitudes, which exposed more snow cover and thus increased reflectiveness of the Earth's surface, as land was cleared for agricultural use. The theory implies that over the course of the Little Ice Age, enough land was cleared to make deforestation a possible cause of climate change. It has been proposed that the land use intensification theory could explain this effect. The theory was originally proposed by Esther Boserup and suggests that agriculture advances only as the population demands it. Furthermore, there is evidence of rapid population and agricultural expansion, which could warrant some of the changes observed in the climate during this period. This theory is still under speculation for multiple reasons, primarily the difficulty of recreating climate simulations outside of a narrow set of land, in those regions, so that one cannot rely on data to explain sweeping changes or to account for the wide variety of other sources of climate change globally. As an extension of the first reason, climate models including this period have shown increases and decreases in temperature globally. That is, climate models have shown deforestation is neither a singular cause for climate change nor a reliable cause for the global temperature decrease. Inherent variability of climate. Spontaneous fluctuations in global climate might explain the past variability. It is very difficult to know what the true level of variability from internal causes might be given the existence of other forces, as noted above, whose magnitude may not be known. One approach to evaluating internal variability is the use of long integrations of coupled ocean-atmosphere global climate models. They have the advantage that the external forcing is known to be zero, but the disadvantage is that they may not fully reflect reality. The variations may result from chaos-driven changes in the oceans, the atmosphere, or interactions between the two. Two studies have concluded that the demonstrated inherent variability was not great enough to account for the Little Ice Age. The severe winters of 1770 to 1772 in Europe, however, have been attributed to an anomaly in the North Atlantic Oscillation,